think I get my sweater.
Also, I don't know if there is too much people. I'll have to open a little. Yeah, you have to. We have something.
Yeah. Don't take a cold. Yeah, no.
Hello.
Hello.
How are you?
I'm good. How are you?
Fine, fine.
Carrying us. I don't know if you're fine.
I run everywhere, but it's good. It's okay.
But anyway, we should make sure that the website is updated at least. Yeah, that's the point. My problem is that, yeah, that's the problem on my life. Yes. And Et donc, tu n'enregistres pas
Pas encore.
Tu es pas
Ça va encore commencer.
quelques petits mégas.
Ah bah oui, c'est moi qui fais le montage, bien sûr.
Moi, j'ai commencé à enregistrer 10 minutes à l'avance.
Ah bah oui, je sais. C'est moi qui fais le montage, je sais. Je m'en suis rendu compte.
Mais non, c'est pour pas oublier, tu vois. J'ai fait
Ah
tout
ouais,
le temps.
t'inquiète. Pourquoi il voit pas la...
Well, I guess that the rain was
Yeah,
not
I cannot compete with the rain.
It's decreasing the
Damping effect of the rain, literally.
Bonjour.
Ok. Tout est prêt. Peut-être faire une...
Maybe we can start with...
La personne sans zoom. Ah, attends, j'ai peut-être fait une bêtise.
I'm sorry? Of course.
Le gars, le dernier email, envoyé vendredi.
Ouais, c'est peut-être moi qui ai fait une bêtise.
Tu as ouvert notre salle.
Ouais.
Il marche pas?
Non,
non, c'est
il a
bon.
ouvert la mauvaise salle.
The density of state.
Bah non, c'est la dernière.
C'est la bonne?
23 septembre.
C'est pierwsze wszystko.
But on the other hand, the entropy is
23 septembre.
increasing, or
Là, tu
at
peux
least it
y
depends
aller.
on the macro state.
Vendredi.
Right. So entropy is the density of
That's what
states
it's on.
when the only thing you know is the energy.
Okay, I see.
If you know something else, then it's smaller.
The blue one includes
And
everything.
then you should compute the density of states for things which have that energy and whatever else you know. And that is a smaller number, and so the entropy is
Ah,
smaller.
il y en a deux
And
maintenant.
it is a asymptote of the.
Ah, ça commence à...
the-
J'ai eu peur.
These, in a sense, are the Jane's entropes.
Ok.
Okay, I see. Makes sense.
Vous voulez qu'on fasse un test ou ça va?
Normalement,
Et
c'est
Monica, tu la vois?
Monica.
Oui, elle est là, je l'ai vue.
C'est bon.
Ok.
Là, et...
Yeah, two books. For somebody here, inside here, then you make a loop.
I'm sorry.
If somebody watch,
C'est normal, c'est mute. C'est normal, on est
if
mute.
somebody watch the
Hello?
lecture in some tablet inside, then you make a loop. Audio loop. Then it grows exponentially.
C'est parce qu'on fait des économies d'énergie.
J'ai ouvert le micro, donc normalement tu nous entends.
Des trucs.
Ouais.
This is a loop.
Allô? Allô?
Monica.
Allô, Monica? Can you hear us? Allô, allô?
C'est quoi, j'entends très loin, je sais pas si c'est moi.
Nous, on t'entend, mais on ne t'entend
Oui.
Allô, allô? Allô, allô? Can you hear us? Okay. No, it's okay, Johannes and Domenico.
So there is a...
Yeah, okay, cool. Thanks.
We can start. What's the But anyway, so announcement for everybody, those people needing a certificate of presence, please send an email to courses at IPhT.fr, please, and we will send you a PDF. Okay, so I think that if it's okay for you, we can start. Thank you very much.
All right, thank you. Thank those of you who are here, have braved today's wet weather. This is, I think, my 10th day in Paris, and I've had great weather up until today when it started raining. So, my plan today is to continue from where we were last time, discussing now in particular entanglement entropy in this basic setup that I started talking about. And I think I will finish that in probably less than an hour, and then I don't have another set of hours worth of stuff to say. So my plan is to stop when we get to the end, and then if I am happy to stick around for as long as anyone wants to ask questions about any related stuff. Okay, so that's the plan. So last time I talked a lot about entropy in general and what I call the James formulation of entropy, of which a special case is that we have some big system symbolized by the rectangular box here, and we are going to cut it into two subsystems, 1 and 2. And as shown in the picture, I'm going to think of 1 as the smaller of the subsystems, in the sense of having fewer degrees of freedom in it, and 2 as the larger subsystem. Also, this is not really necessary, but I'm going to think of the picture as showing something that's in real space. So there's a subsystem 2, which has a volume V2, and there's a subsystem 1, which has a volume V1, and V1 I want to think of as being smaller than V2, but also that these pieces are localized in space so that there is an area of the boundary Okay, so in particular, this area of the boundary notion wouldn't apply to something like the SYK model where everything is coupled to everything else. So I'm focusing on a lattice spin system or something like that. We could also do this in 1 dimension, but I'm going to think of it, and then the area would not really have a meaning. It would just be the single points at the end of the subsystem 1 line. So I want to think of being in 2 or more dimensions. Okay. And so the Hamiltonian will split up into a Hamiltonian of subsystem 1 that references only the degrees of freedom in subsystem 1, similarly subsystem 2, and then a piece that couples them together, which I want to think of as, in some sense, living on the boundary. Okay, and then we can consider tracing out the degree, and we're going to be in some pure energy eigenstate of the total Hamiltonian, and I'm going to consider tracing out the degrees of freedom in subsystem 2, leaving over a density matrix for subsystem 1, or we could trace out subsystem 1 and leave over a density matrix of subsystem 2. And it will be convenient to define energy eigenstates of the individual subsystems and to separate which one we mean. I'll use a lowercase letter for the smaller subsystem and an uppercase letter for the larger subsystem. And where it won't cause confusion, or where I at least hope it won't cause confusion, I'm going to drop these indices on the energies. Okay, well. All right, and so now, just completely generally, if we have a pure state, not necessarily an energy eigenstate, we can always expand it in the basis of the subsystem of energy eigenstate. Okay, and I said last time that, again, very generally, if we start with a pure state of the whole system and we construct these subsystem density matrices, that in fact the eigenvalues of rho 1 and rho 2 are the same, except that rho 2, being larger, has more eigenvalues, but the extra eigenvalues of rho 2 are all 0 in that case. So, yes.
This decomposition of the pure state in terms of this tensor product, this does not get affected by the h12 degrees of freedom. Is this because?
No, I'm assuming that I can, again, the simplest thing to think about is something like a lattice spin system. I'm assuming I can assign every spin to either subsystem 1 or subsystem 2, and then H1 is all the terms in H that only refer to the spins in subsystem 1, and H12 is all the terms that have one or more spins from 1 and one or more spins from 2. But the complete set of, I can now talk about a complete set of states in terms of eigenstates of each individual spin, which then would be mixed. Spins in subsystem 1 would get mixed up to be the eigenstates of H1 and so on. But it's still a complete set of states. So let's see. Last time I made that assertion about the eigenvalues, but there's actually a fairly easy way to see it just from this structure. So let me do that. If we look at rho 1, we can write this, or rho 1, we can write this okay, so I'm basically now just writing it with indices instead of writing out the explicit states. And in a somewhat more schematic notation, we can think of this as dagger. Similarly, rho 2 rho 2 looks like dagger M. And so now, if we imagine computing the trace of a power of rho 1, I'll compute a string of n daggers, but on the other hand, we compute trace rho 2. This, but now just by the cyclic property of the trace, I can move this M to here, and we see that the traces are equal. So the trace of any power, at least integer power of rho, of either rho 1 or rho 2 is the same, and if they were finite dimensional matrices, that's enough to prove that the eigenvalues have to be the same. in an infinite dimensional case, we in principle have a moment inversion problem. And I think there are weird special cases where it doesn't work. But my ideology is always pretend the Hilbert space is finite dimensional, and if it's really a spin system, then it really is finite dimensional. And hope we don't run into any of the issues that can come up in the infinite dimensional. Okay, but now, all right, so that's the statement. All right, so again, so this implies that the eigenvalues match okay, but I want to come back to this. So this has been extremely general. This works for any pure state. But now I want to specialize to this case that I said we were talking about. And I want to think about, what can we say about this matrix? So Josh Deutsch in 2010 said, well, we should think of this as a random matrix, again, in the spirit of Berry and random matrix theory more generally. But of course, it can't be exactly a random matrix. And this idea was picked up by Peter Liu and Tarun Grover, I think 2019, who wrote down a somewhat more specific model for how the matrix should work. So I'm just going to write down their model for this. So here I pulled off what is essentially a normalization factor of 1 over the square root of the total density of states, which we'll see is the right normalization factor because trace rho 1 and trace rho 2 both have to be equal to 1 by usual state normalization. Then there's an idea that these two subsystem energies should be close to the total energy because the two subsystems are most of the total. Again, I want to think of this interaction Hamiltonian as being small in some suitable sense. In particular, it lives on an area instead of in an extensive volume. So E1 and E2 should sum to E pretty closely. And being really technical, I want a square root there. So this is supposed to be a smeared Dirac delta function that tells us that the two energies should match. And what should the smearing size be? Well, that was worked out by Chaitanya Murthy and me. Again, I think in 2019. We were able to show that the smearing length or smearing width of the delta function is just controlled by the expectation, the variance in this particular energy eigenstate. So these angle brackets here mean sandwich between of the interaction Hamiltonian, which is it has to be that, right? Because what what allows this energy subsystem sum to differ from the total is precisely the presence of an interaction. Otherwise, they'd have to be exactly the same. And so it's not a surprise that the width of the approximate delta function here is controlled by this. And furthermore, again, in this situation where we think of H12 as living on the boundary and also being local along the boundary, one can argue, and I refer you to our paper for the details of the argument, that basically this variance will be due to a variance of each term in H12 along the boundary, and then when we sum to get the total, we'll get something that scales like the area of the boundary. So most of the time, and what I'm going to say from here on, I'm going to treat this as negligibly small, and this is a real delta function. But this is where area corrections to various volume entropies that we'll write down appear if we track them through closely. Okay, and finally, I have this C here. Okay, and now I want to think of C as a random matrix. So I haven't really done anything except state that there should be something that's setting the size of the matrix elements appropriately. There should be something that's telling us that the two subsystem energies have to add up to the total energy, approximately. And so the C matrix this we will think of as a random matrix with mean 0 and variance 1 in the way I have often written other random matrices.
Question?
Yes.
So this is an assumption for any kind of Hamiltonian? Or?
Yeah, this is an assumption. So again, this is in the spirit of ETH, and that we have our total Hamiltonian is going to be, quote, chaotic, unquote, by whatever your favorite diagnostic is, which could be that this looks like a random matrix. So that's the ETH assumption, that this will look like a random matrix.
Or any kind of Hamiltonian? Or?
Not for any kind. I mean, if I give you some integrable Hamiltonian, then this won't be true. The matrix will be controlled by the conserved quantum number. So yeah. So I should have said I'm assuming, because right, this is my shtick, right? ETH. I'm assuming a chaotic Hamiltonian. All right. Oh, let me just briefly say, how do we get this? Again, this is really one of the more technical points, but this follows from noticing that H12 squared is really the same. So this H is acting on the state E, and so we can just replace this by E, and then each of the individual H's can be similarly replaced, and et cetera, and and then one eventually shows that that will become the width of this delta function. All right. Okay, so now having done all this, what can I erase here? I'll leave my picture up. Okay, so rho 1 ik is given by that expression up there. Now I want to substitute in this. So we get And now, of course, what I want to do is say that this is delta IK. But if we're being careful, its statistical average by definition is just delta IK. But if I really look at it term by term, there'll be some exponentially small terms that are suppressed. And because we're doing the sum over subsystem 2 here, it's the density of states of subsystem 2 that's important. So there are going to be corrections to both the diagonal and the off-diagonal pieces that look like this.
Excuse me?
Yes?
I'm a bit confused by the indices in the delta function in the upper board. If I understand correctly, I refers to an eigenstate of part 1, J refers to an eigenstate of part 2, right?
Yes.
Then delta Ij, what's the meaning?
Oh, maybe I wrote something wrong.
Maybe there's some permutation.
Oh, sorry, that's a mistake. Oh, this is completely wrong. No wonder nobody understood. No, still wrong. Okay, boy, my brain will just not write. Sorry. IJKL, who can tell the difference? Thank you. Yes, that was bad. Yeah. Okay. I did manage to write IK over here, so. All right. And now, having done this long story about how big the width of the delta function is, I'm going to go ahead and set it to 0 and treat this as a real delta function. And similarly, again, as we've done before, think of the sum over J as an integral over the energy of subsystem 2 weighted by a density of states. And okay, but the energy of subsystem 2 is restricted by this delta function, and so let's see. Okay. So let's see. So now it's approximately diagonal, but with some exponentially small corrections. And E again is the original total energy of the system. E1 is the energy of subsystem 1, which is, you should really put an I on here as that index. So. Okay, and this sort of formula for the density matrix of a subsystem was proposed earlier in 2016 by Morsky, Kari, and Liu, and they called this Ansatz subsystem ETH. The idea being, the story I've been telling about ETH is in terms of matrix elements of observables, but again, we can regard subsystem 1 as the complete set of observables that live in subsystem 1, and so if I know the reduced density matrix of subsystem 1, then I implicitly know all the expectation values. So this is just a way to summarize ETH for a particular set of observables, and this was their answer. And so you'll notice it doesn't have any e to the minus beta h's in it, we could get an e to the minus beta h by Taylor expanding near this energy. There's one energy in which subsystem 1 has as much energy, well, has the expected amount of energy by essentially equal partition of energy, and then Taylor expanding about that will give you an e to the minus beta h formulation. But this formulation, they said, and I agree, is in some sense more fundamental in that it's really just referring to densities of states. And we can think of e to the minus beta h's as just approximations to these densities of states.
Question? Yeah. So in the way you proposed ETH, it seems that there's a notion of looking at the system at long times, but here there's no time.
Well, I mean, an energy eigenstate is in a sense an infinite time thing, right? Because if you right. So if I start with some state, any state you want, right, and then I time evolve it for time t, but then I pick some energy I like and multiply by e to the it, and I integrate over all time, I will now get a delta function. Be formal here, right? Okay. So and now this, we could argue up to some that we're now projecting onto an energy eigenstate. So the sense in which an energy eigenstate is an infinite time thing. And so the way I like to think about ETH is your matrix elements of observables in the energy basis have to have that structure that I always write down, and if they do, then the time dependence will work out so that the system looks like it thermalizes according to those observables. Okay. So here, this is really the same story, but instead of talking about energy eigenstate expectation values, I'm looking at the density matrix of a particular subsystem. But from this, I could compute all the expectation values of all the observables that live in subsystem 1. So this is, in a sense, a more compact and efficient statement of what ETH means.
Sorry, just to understand correctly, you have S2 in your exponential S2. So in this approximation, S2, the entropy, is equal to the full entropy. Otherwise, if you Taylor expand, how do you simplify e to minus si?
I'm sorry.
In the formula Dimarsky, no, in the there, upstairs.
There.
Yeah. You have S2.
Yes.
And in this approximation, S2 is equal to S. I mean, if you Taylor expand, do you simplify S2E with SE?
If you hold on a bit, I think I'm going to do some stuff where I think this will become clearer.
Okay.
I think I'm going to do that soon. Oh, but I have one other comment first. We could have done all this swapping subsystem 1 and subsystem 2. I could have traced over the smaller subsystem. And what goes wrong in that case is that if you then ask about the eigenvalues of this matrix, it's really an assumption, I guess. The assumption is that if we trace out the larger subsystem and get this density matrix of the smaller subsystem, that we can now really ignore these exponentially small corrections, and that the eigenvalues of this matrix are correctly given by just the diagonal term. On the other hand, we know that can't be true if we trace out the smaller subsystem, because we know that the eigenvalues of rho 1 and rho 2 actually have to match up to extra zeros. So in order to be able to neglect these quote, small, unquote, off-diagonal terms, we have to have traced out the larger subsystem. If we trace out the smaller one, we would still get this formula with the 1s and 2s swapped, but if we then ask what are the eigenvalues of that density matrix, there would be a secret conspiracy among these guys to change them and not give us what we think we get just from the diagram. And this will become important.
Question?
Yes.
Is there a limit to this process? Like how small can I make the subsystem 1?
Oh, well, okay, so you can make it. I think at this level you can, if you don't care, well, if you want to say that, if you want to write this down as the density matrix of subsystem 1, I think we want subsystem 1 to be pretty big, right? Certainly I want to be able to neglect, I want to be able to set delta to 0 here, and if subsystem 1 is small, then it's not going to be small compared to the boundary, and I won't have been allowed to do that. So I'm assuming that subsystem 1, I mean that was implicit in writing down the Hamiltonians, that the Hamiltonian of subsystem 1 is in some sense, and I guess we can quantify this. So we want to say that if I take, and now again, angle brackets are denoting energy eigenstate expectation values. I want to say that H1 is going to be approximately. Let me introduce this notation. So F will be the relevant volumes of the two subsystems. It's. I don't even really want. I really want the variance of H1 too is the thing that really matters. But in any case, I want all of these things. I want this to be small. So I want much more energy in subsystem 1 and subsystem 2 than. So I mean, I could scale this to be 0, but. I want this to be bounded by something like the area, and I want to think of that area as much less than a pi. And E here, I'm assuming, as always, is an extensive energy that scales like pi. Okay. All right. So this is my. I'm really messed up. Blackboard here. Let's try to clean it up a little bit. And we could call this the subsystem ETH ansatz for the density matrix of the subsystem. Okay, let's try to compute the trace of rho 1, which is supposed to come out to be 1. All right, so let's see if it comes out to be 1. This e to the minus s of e, the constant, the trace, the trace is over the degrees of freedom of subsystem 1, So I convert the trace to an integral over the energy of subsystem 1 with a density of states factor. And then I have e to the s2 of e minus e1. And my claim is that on the basis of understanding what we mean by densities of states, and up to the approximations inherent in this, that this is indeed 1. Because what is this doing? This is counting the total number of states by saying, okay, if I have energy E1, I have this many states in subsystem 1, and I have this many states in subsystem 2. If I multiply them together, that's the total number of states in the combined system. And now I'm going to sum over all the ways of distributing the energy. And that should just give me the total number of states of the total system, which by at that energy, which by definition is just e to the s. Now, of course, one can attempt to do a better job on this and worry about prefactors and stuff like that, all of which I am not doing. But now to come to your question, I think this will help with your question, Ricardo. Another way we can also do this integral by Laplace's method, because everything is supposed to be large. So I can take the derivative of the exponent and set that to 0. And so we evaluate the integral by asking where is the exponent stationary, and then the integral, again, not worrying about prefactors, is just the integrand evaluated at the solution of this. But this, of course, is just telling me that the derivative of s of E1 is the same as the derivative of s of E2, where E2 is fixed by this to be E minus E1. And because it was a minus sign here. But what is this? This is just the temperature, inverse temperature of subsystem 1, and this is the inverse temperature of subsystem 2. And what this is telling us is that at the energy which is most likely, or which dominates this integral, the two subsystem temperatures are equal, which makes perfect sense physically. Okay, so does that help, Ricardo?
Okay, yeah.
Yeah. All right. So these two inverse temperatures are equal at the point of, I still want to call it steepest descent, but whatever it's called. And so we can call the solution E1 bar, and then S1 of E1 bar, we can call this S1 bar, the entropy of subsystem 1 at the most likely energy, and of course E1 bar and E2 bar add up to E, and the derivatives, again evaluated at that energy, I will now just call beta the inverse without a 1 or a 2 because they match. And so the two derivatives match and are equal to the what we would call the inverse temperature at that point. And so then, evaluating the integral in that way, we get e to the minus s of e, and then e to the s1 bar plus s2 bar. But again, now, at this even somewhat cruder level, again, the entropies of subsystem 1 and 2 add up to the total entropy. So at the level we're doing this integral, we again get 1. Okay. All right. So this is kind of a warm-up calculation to compute trace row 1, which is supposed to be 1, and which I claim it is to the level of the approximations we're doing. But now we would like to compute trace row 1 to a power as a starting point to eventually get to the entanglement entropy. So at the same level of approximation, you can try to compute, well, before I compute the trace, I'll just compute row 1. Whereas row 1 was up there somewhere. So it's e to the minus n s of e to the n s2 of e minus e1. Get the trace of row 1 to the n. Again, we'll do the same integral. This is exactly what we were doing before, except now there's an extra n in front of S2 and also an extra n in the prefactor. Okay, but now there's a punchline, which is that this is not completely correct. And the reason and this was one of the main points of my paper with Chaitanya, the reason it's not correct is that when we imagine doing this integral over E1 and E2, sorry, just E1 at this point, imagine doing the integral over E1, if E1 is very low, S1 is low, but if E1 is very high, then S1 can become big. And because here we have E minus E1, when E1 is large, S2 might become small. So there, in principle, and even in practice, there's a regime of E1 where even though E1 is the smaller subsystem in volume, we are imagining partitioning the energy in such a way that we've given a lot of energy to subsystem 1 and not so much to subsystem 2. And at those energies, subsystem 1 has more states than subsystem 2. And if subsystem 1 has more states than subsystem 2, we should not have traced over subsystem 2. We should have traced over subsystem 1 to avoid the extra zeros problem. And so what that means is that this is wrong as written, and that, just realized there's a giant box of colored chalk here, which I haven't been using. The correct thing to put here is that we always want to be tracing over the smaller subsystem at the final trace. So we should replace this with S min plus N S max, where S min is the smaller of these two guys, and S max is the larger of these two guys. Okay. And this was actually first noticed by Lev Vidmar and Marcus Riegel. I think 2018. I won't write the year because I'm not sure. They were doing a numerical calculation in a system that had another conserved quantity, and they noticed this phenomenon well, I'll show you in a minute what answer you get when you make this replacement. But they found that same phenomenon in another conserved quantity, and they understood that this was the problem, that you should always be tracing over the locally in whatever quantity of interest, here energy, you should always trace over the larger subsystem. And if you put too much of your quantity in the smaller subsystem, you have to do it like this. Okay, so now well, entanglement entropy is defined as a suitable limit of this. Right, so, I mean, we can also consider the Renyi entropies, but I'm not going to do that here. So that's the definition of the entanglement entropy. But we can now just look at this expression and take that limit. So I claim when you take that limit, I'm not going to go through the details. One gets this formula, which is essentially S bin, although not exactly, so I don't want to call it S bin. Okay, and then to evaluate this, we again want to do an expansion around the point which okay, and where again E1 bar is the point where this exponent is stationary. Okay, and of course, similarly for S2, they both have the same beta. This second term is heat capacity, and we're again going to assume that everything scales appropriately. Well, for the energy, we can just show that it's true. Where F is again the volume fraction. I guess I might have erased it. And that this also applies to the heat capacities, which also scale like volume. All right. So if you do all that, then what you find is the entanglement entropy is, first of all, the most important term is just what you would expect. It's the appropriate fraction, the fraction that denotes the smaller subsystem of the thermal entropy. So this is just saying that the entanglement entropy of the smaller subsystem is just the appropriate fraction of the thermal entropy of the whole system. This is another way of saying that the subsystem has thermalized. Now we're saying that it's thermalized by looking at an entropy rather than looking at expectation value of some observable. But all this song and dance about being careful about which subsystem is the smaller leads to a correction, the same correction that was first seen by Vidmar and Riegel. And so I am now plotting the entanglement entropy as a function of f from 0 to 1. And mostly, so first let me, so if we didn't have the correction, it would just be this pyramid structure, maximizing at a half S of E, but actually the correction rounds it off, so it doesn't quite become a peak. And the gap here has a nice formula. It's just the square root of the system's heat capacity over 2 pi, which scales like the square root of the volume. And of course, S itself scales like the volume. So this is a root volume versus volume effect, so it's small. In 3 or more dimensions, it's even dwarfed by the area corrections, which I've completely dropped all area corrections. There's also an area correction here. But this one was novel and was not appreciated early on, that there is this effect. And this really comes, I would say, as a true entanglement effect, in that you really, to get this, you have to know that you're always supposed to trace over the larger subsystem, even locally in energy. And that, knowing that you have to do that, it feels to me like a sort of hallmark of entanglement. So the expectation on the basis of that idea, always trace over the larger subsystem, produces this correction, and again, this has been seen numerically, so it does appear to be an effect that's actually there. Okay, and I've almost used up an hour here. So this is the story I wanted to tell you today. This is a more technical and closer to current research-related issue of how entanglement entropy appears and is characterized in chaotic systems. And by chaotic, I again just mean something that can be modeled by these random matrix ideas. And that's really all I have to say. So I am going to stop here, and we can take a break. And if anybody wants to ask more questions, I would be happy to answer questions for as long as there are questions. So break for 10 minutes, and then...
10 minutes break, okay.
Okay, 10 minutes break, and then I have nothing further to say except answers to questions. So We'll see what happens. Thank you for your kind attendance and attention for this whole series.
So, okay, we are back. And I don't know.
You don't know if there are any questions here? Oh, we have it. All right, a question.
No, just can you say a few more words about this gap proportional to root of the heat capacity? Is there some physical intuition where it comes from, or?
Yeah, no, we don't. I don't have a good physical intuition of why it's, the square root of the scale, like the square root of the volume. It comes out of this calculation, and mathematically you can see that, well, it's going to have to be related to this, but I'm not even sure I would have. And it has to be smaller than the volume because, okay, so it's related to C, because you can easily see that if you don't have a C term in the expansion, that this effect isn't there. So it's necessary to have the C term. And once you have the C term, and and C scales like the volume, and the correction has to scale like less than the volume, square root. That's what the math is going to. But I do not have a good physical intuition. I don't even have a good physical intuition for not only how does it scale, but sort of what does it mean physically.
Mm-hmm.
I was saying at the end, I was just throwing out words saying this is some sort of entanglement correction to the thermal entropy. I think, okay. But do I have a better mental picture that goes with those words? I don't.
Mm-hmm. Has it been observed or confirmed in numerics? For
yes. In a slightly, and it was originally discovered by Marcus Riedel and Lev Vidmar in numerics. I mean, they were trying to confirm the sharp triangle, and their numerics kept not getting up to the triangle, and they kept, okay, what's going on? And they figured out the basic answer, and which is this, you have to trace the larger subsystem. And so, my work with Chaitanya Murthy is sort of systematizing that a little bit, but. So if we have a general formula for what happens if you have multiple conserved quantities and so on, but it's basically the same thing. The square root of some object that can reasonably be called the average heat capacity across different conserved quantities.
If one would do the same calculation for a thermal state, one should expect that it's the same result, or?
Yeah, I mean, so for a really thermal state, I think for a really thermal state we would just declare that it's this, and we would not make this substitution because we would have no reason to make that substitution. Right? I mean, this substitution saying that I should trace over the larger subsystem. If you've just declared that you know what rho 1 is, and you know it's thermal, and thermal we could interpret, as subsystem ETH. So we could just declare that rho 1 just is. This is sort of the slightly fancier meaning of thermal. If we just declare that this, or you can go ahead and say this is. I think if we do it carefully, we would get something like this. In some call it in some approximation. If you just declare that this is the answer. Then when you go to do this computation, you would do the version that I said was wrong in the pink box, and you would not get this correction. Right? And so you wouldn't even see the turnover. Right? You would just go like this. Right, so it's really entanglement. The statement that it's an entanglement entropy is, or a reduced density matrix that you got by tracing something out is what tells you that the curve turns over, and then the slightly more subtle effect is that it doesn't turn over sharply.
So here we haven't talked about dynamics yet, or can one answer questions related to dynamics, like how does the entanglement grow in the system?
Oh, yeah, well now, yeah. So at this level, we're not trying to answer questions about dynamics. And again, as we were saying earlier, the fact that I've declared that I'm starting with an energy eigenstate of the whole system means there's no dynamics, right? An energy eigenstate just sits there. That, by the way, is a slogan way to understand ETH. We know that an energy eigenstate doesn't do anything. Well, a state of thermal equilibrium doesn't do anything. So an energy eigenstate is a state of thermal equilibrium. That's basically ETH, short version. But, right, so to have some interesting dynamics, we would have to start with an initial state that's not an energy eigenstate, and presumably we want to do something, like localize it in subsystem 1 and then watch it spread out and so on. And, these kinds of things are studied, I don't know if they're studied in this context so much.
Just one question about the notation. When you wrote the integral over E1, but I mean E1 only if you have to trace over the bigger system. So if they switch, it should be a E2, something like that.
Yeah, really, right. So if it switches, you should really call it E. So at this point, if we've had to switch, then it's really E2, and we've just renamed it for mathematical purposes E1. But
okay, but
we should probably change it to something like E min. Maybe this would be better.
Yeah, I'm happy with that. All the one is say min or minus, whatever.
Yeah. So by the time we make this substitution or change, E1 is no longer necessarily the energy of subsystem 1. It might be the energy of subsystem 2.
Okay.
Yeah. So bad notation.
No, but anyway, it's a dummy variable, but
it's just a dummy variable, psychology. Right? And it's exceptionally dumb in the case where it should have been E2.
Perhaps there is a rough sense in which this plot that you showed of the von Neumann entropy can be mapped to the page curve. I think you were commenting on it.
Well, there's a sense in which this, the problem with the page curve is that, again, if we just declared that rho 1 was thermal, we would just get this curve, right? And it's because we know it's really entanglement that it does this, even before we worry about the correction. So this is really very similar to Page in that, Page is saying, in this sense, this is really exactly the same as Page. Right. So the fact that it turns over is exactly the Page curve. But this correction would not appear, does not appear in the Page curve, because it's a result of having a density of states that varies with here energy, but more generally any parameter. So Page's original thing was completely featureless system, just grab a subsystem of some dimensionality. And so in that case, all these S's, something like e to the S1 of E1 would just be the dimension of subsystem 1, for example. Okay. But now there's no variation with energy. So when I do my integral over energy, everything's constant, and so this just produces some constant factor of D1 again. So this property that which subsystem is larger or smaller can depend on the value of some parameter that you're integrating over or summing over. needs to be there for this effect. And one reason it wasn't seen originally in various numerics is that this entropy formula, where we're expanding around some mean entropy. So this is the conventional definition of heat capacity, but a lot of numerics is done in spin systems in the center of the spectrum, where the temperature is effectively infinite. So in that case, beta is 0. But in general, there's still a term like this. So as beta goes to 0, C goes to 0, which is, physically that's also true, right? At infinite temperature, the heat capacity is 0, because if you change the temperature, it doesn't matter because it was already infinite, basically. Okay. So in the sorts of numerics that are often studied of center of the spectrum of some of the spin system, the heat capacity is 0, and so there's no dash. Lev and Marcos were looking at a system where they had a conserved quantum number, and they were interested in effectively chemical potentials away from the center, and in that context, they saw the gap. And they first saw it numerically and then said, why is there a gap? This is basically their explanation, but translated to energy instead of the particle.
What happens when we take the specific cases of systems close or at a phase transition?
Yeah, well, if there's some sort of structural thing happening in your energy eigenstates, then you can't use these simple random matrix models. So you have to have some model of my M matrix that's appropriate to that situation, and presumably it's not just a simple random matrix. So we have to do something more clever.
So more questions?
No.
And online people, do you have questions? Do not hesitate to switch on your microphone. Okay, so they hesitate.
All right.
Okay, so thank you, Mark.
Thank you again. Thank you.